Let's talk about the second part of the two-step variant calling process that we recommend for germline short variants, which is this GVCF-based workflow, which we've been talking about quite a bit. So now we're going to dive into the specifics of how it works. Okay, so you're going to start knowing this particular diagram by heart at this point, our overall best practices. So at this point, James has walked us through what we're doing per sample with haplotype color. Now I'm going to talk about the second part where we're consolidating GVCFs and joint calling them. All right, so again, you've seen this one before. Laura made the case that when we're looking at germline variants, we want to look across populations. This is going to empower us in many ways. I'm going to talk mainly about the way this empowers us from a technical standpoint for the variant calling process. There's a few things that we get from the joint calling. One of them is it really helps us deal with errors or just when the data is not obvious. We've talked about the fact that for short variants, in many cases, it's true that you can pretty much call the variant just by looking at the pileup of bases, pileup of reads in IGV, for example. And you can see pretty clearly if there's nice, good, even balance between the alleles, there's clean data, there's plenty of coverage, you can say quite confidently, yeah, that looks like a variant. But there are many cases where that's not the case, where there's low sequence quality or low sequence coverage. That's a big problem. And one of the things is that if we look at this, this is an example with a few samples. If we look at just sample number 1 here at the top, you see that I don't have a lot of reads. I just have 6 reads, which is kind of low. And I have 4 of them that are the reference allele A. Then I have 2 of them that are a variant, possible variant allele G. But that's really not enough evidence. It's not quite half and half. It's not very distant. But honestly, at that coverage, just 2 reads, that could just be an artifact. And so with that amount of weak evidence, it's very likely that we would just filter that call out. We wouldn't call that as a confident variant. So we may miss it. Now, if we look at other samples, in addition to that one, there's a chance, if it's a real variant that's in the population, if we have enough samples, there's a good chance that we'll see this variant again. And for example, here we have some number of samples, eventually, and many of them may be reference at this position, but then we get to another sample that has kind of the same pattern. And if we're seeing the same thing, and it doesn't have to be exactly the same counts, but if we're seeing the same allele also represented in there, then that kind of raises our confidence because it's going to be more likely that it's actually a variant that's present in the population as opposed to an artifact that manifests in exactly the same place in the same way in unconnected samples. And so that's one of the reasons why we want to look at multiple samples when we're doing the germline calling. Now, of course, if you're looking at common variants, you don't need to use a lot of samples to get that other person who also has that allele. But if you're looking for more rare variation, then you're going to have to look at a lot more samples. And that's where you get in the territory of having tens or hundreds of thousands of samples potentially if you're looking for things that are very rare. Okay, but that's the basic concept. Any question?
Once you have, let's say, 100,000 samples and you do the joint calling, why do you have, and let's say that that's determined sufficient to cover the population, why do you ever have to do this again? Why can't you just use the results of that and say, okay, that's all of the common variants, and now let me compare my variants to that?
Yeah, so there's a couple things. So why do you need to do that again? Do the variant calling again? There's a couple of different things. One of them is you actually need to reevaluate that evidence for the samples together. ideally, because you might have something that in your original cohort was not, you didn't find another person, and it doesn't make it on through to the final list of variants. But now you're finding another person, it might actually help pull out this original thing that you had missed. That is a possibility. Now, that being said, there is a resource that is kind of similar to what you're talking about, which is Nomad, which is this massive call set that was made on, I forget how many we are at this point, but it's over 100,000 samples. And it's very useful for analysis. You can't necessarily, right now it's not trivial for somebody to just join call against Nomad, although that would be awesome to enable. But you can still go with your call sets and compare it to Nomad and see if your thing, your variant of interest, is present in there. But I digress. That's kind of a different usage of that kind of resource. But there are efforts to make that kind of resource available for analysis, if that makes sense. Yeah. Okay, but let's stay focused on this particular aspect of the joint calling, the very technical advantage of seeing the data, seeing the evidence for or against a variation. One of the things that we want to be able to evaluate while we're doing the calling and later actually the filtering, so this is foreshadowing the next step of variant filtering a little bit, is that this is going to help us evaluate whether what we're seeing is, in the case where it looks like there's evidence for variation, whether it is actually evidence of variation or whether it is artifactual. And in this case, we're representing a stack of reads that are present at this position. And if you just see that like that, well, you see some C's among a bunch of A's. Like, okay, well, is this potentially a possible variant? Now, if we break down which alleles are present on which strand orientation, that is actually quite illuminating. Because if you look at, so the forward reads are the blue reads, and the reverse reads are the orange reads. If we break down how things are distributed on this read, we see that the reference allele is represented on both forward and reverse reads, which is great, which is what we expect. But this variant allele here, the C, we're only seeing it on the reverse reads. We're not seeing it on any of the forward reads. Now, that might just be because there are fewer forward reads, and we just didn't happen to catch any with the variant allele. But that could also be a sign of an artifact. And we know of various types of artifacts that cause strand-specific allele artifacts. So being able to do this breakdown is useful on one sample, but often with one sample, we don't have quite enough information. We might just have kind of something that happens by accident for this one sample. But if we have multiple samples, then we can see if there's patterns of bias in the data. And so we'll look, for example, across all of the samples we have, which is going to give us a lot more data points than for just that one sample. If we look across all of the samples, we'll be able to see, because there's an evening out of the distribution of these properties, we'll see that maybe, yes, there is a strong bias in terms of the alleles, that the C's are really represented at a much lower fraction than we expect if there's even distribution, or that there is not. If there is bias, that's something that we'll annotate and we'll flag so that later we can potentially filter on it. If there's not bias at this stage, we can also look at strand bias. And again, this is kind of an extension of the earlier example. If we find that, let's look at the healthy case here, once we look across many samples, we see that actually we do see that C allele on forward and reverse reads once we're looking at multiple samples. And in that case, we will feel more confident about this variant. But then if we look at the unhealthy case, where this is pretty much verifying that across multiple samples, we have the same pattern of not seeing the variant allele on any of the forward strand reads. That is going to tell us that there's actually a recurrent artifact at this site that we should not trust. So it's not just seeing evidence of variation in multiple samples. That's not sufficient to be satisfied that it's real. There's also looking at and looking for evidence of bias to see if that might actually just be a recurring artifact. So that's going to be part of the process. And that's part of the information that doing the analysis across multiple samples affords us. Any questions at this point?
Yeah, question. So can you explain why the strand bias, the yes part, needs to be filtered out? Why couldn't it actually be real? How do you distinguish between a real thing happening on only one strand and a bias?
It's really difficult, and that's why we have sophisticated filtering approaches, because it's true that you could still have something that by accident happens to be that way. And so we'll talk more this afternoon in the variant filtering part about how we can use statistical models to evaluate basically how worried should we be about this particular thing. And we'll see that there are, in some cases, variants that are real that show bias, but bias in only one dimension, for example, but versus others where there's multiple things that look wrong about the call are going to lead us to filter those out. Any other questions?
Perhaps you said this, but is it possible that strand bias exists and that it is really a variance?
Yes.
Only going one way versus the other?
Yes, so it is possible to, by accident, only have biased evidence for a real variant. And that's where the variant filtering is really tricky, because it's going to be very difficult to say one way or another. It's going to be about distribution of statistical probabilities and modeling. Yeah. Okay, all right. So finally, and this kind of goes to a question that was raised earlier, the key thing in terms of what we're producing in the VCF output with that reference confidence in the GVCF output is that we're going to have that super important information about if we're not getting a variant call, is it because there is good evidence that there is no variation, or is it because there's insufficient evidence either way? And that's going to be quite important for the interpretation. Now, to walk through this example, we've got read data from sample A and sample B, two different people who are being tested for predictor markers that are indicative of risk for Alzheimer's. And so basically, if you have variants in those loci, you are at higher risk of developing early onset Alzheimer's, if I recall correctly. And now, if we analyze either of these people's sequence individually, we're not going to make a variant call in either case. So in the final VCF, there's not going to be a record for that site. But it's for very different reasons. Sample A, I've got excellent sequence data. I've got excellent coverage and quality. I'm very satisfied that this person does not have this risk factor. Sample B, that's not the case at all. Something went wrong with the sequencing, even though this was whole genome and good coverage and all of that. But for whatever reason, I have a hole in the sequence right here. And so I can't say either way. And again, in the final VCF, I would not have any information about that. So, and I would have to maybe do a coverage analysis separately or something like that. Now, if we're doing a joint analysis, and especially if it's an analysis with other samples who are you can essentially have positive controls of people who have variation at that locus. In the final cohort VCF, you will have a record at that site, and for each person in your cohort, you will have the qualified information of, do they have something, how likely is it to be real, or do they not have something, and how likely is that to be correct call? Okay, any questions about that? No, okay. All right, so that's what we're trying to achieve. How do we do it? James already outlined this process. The first part is calling haplotype caller in GVCF mode, so running through this process individually for each sample, making a GVCF for each of them, and then getting to this joint calling part, where the analysis is going to be done across all of the samples based on the GVCFs. So how does that work? To show you a little bit more detail about what the GVCF contains, what we're producing, what haplotype caller is producing in GVCF mode, is this fairly large file. It is a VCF file of a particular type, and it has the usual, in yellow you see the usual variant call records, where at this particular site we found that there was a possible T allele variant. But then there's also these blue records, which are which we're calling reference calls, where we don't, or non-variant calls, where we don't have evidence of variation, but we record what we did see. And we're using this non-ref allele, this symbolic allele, to basically act as a placeholder so that we can have Phred scale likelihoods of the homozygous reference case, okay? And also, well, the homozygous reference case and the non-ref. So this is really symbolizing the kind of the residual chance that this call might actually be a variant. Does that make sense? Okay, so we have a mix of these two types of records. Both types have the non-ref allele. And that's really the easiest way to recognize a GVCF, is that it has those non-ref alleles in it. Like I said, they are VCF files. They follow the VCF specification. You have on the left a regular VCF with the classic header and then the records. And every record in your regular VCF is a variant site record. And haplotype caller GVCFs come in two flavors. The one we generate by default has, of course, the variant site records, but also these non-variant records. Now, the detail here is that they're block records, as opposed to, we are able to make what we call base pair resolution GVCFs, where you have actually a separate record for every single position in the territory you analyzed, potentially your entire genome. But that gets to be very, very large file. And so we compress that into blocks based on if they have the same level of confidence and data quality within a certain span, we compress that into a single block record just to keep the files manageable. Yeah?
What's the size of that file compared with a BAM file?
Compared to the BAM file, it's much smaller. I don't want to hesitate to give a number. Do you want to give numbers, Laura?
I'm dyslexic, so I don't like to quote numbers, but it's a lot smaller.
It's a lot smaller is the definitive. How about we answer you in the Slack channel? I don't want to give you a number that's wrong. I personally don't work with full-scale files. I do little snippet examples. Laura's the one who deals with these huge files on a daily basis. So I'm going to blame her for not having a definitive number, but we'll get you one on Slack or in the YouTube comments. Okay, so those are the file, what's in the file of what you get from haplotype caller. And so the joint calling process is going to run through all of the GVCFs. We've talked about that. In the final VCF that's produced, you don't have any non-variant records anymore. By default, you just have the definitive variant records that have been determined based on the joint analysis. Yes. There is an option, I believe now, to emit non-variant records as of the 4.1 release, I believe. Yeah, so since the recent version 4.1, we now have the ability to still emit the non-variant records if you really want them, but that will make a very large file. So you want to make sure that you want that before you make one. Okay, so in practice, in the nitty-gritty, there are two steps to this. The consolidation step is really just a technical piece that allows us to deal with the amount of data that's involved. Because if we're running on especially hundreds or thousands or more samples, we don't want to have that many files open at the same time. So we don't want to run the tool on all the files at the same time. So we're going to consolidate the files. And there's two ways to do that. In the old GATK 3, we had a tool that just hierarchically combines the files into one mega GVCF file. But that's very slow. It scales very poorly. And you have to do it in batches of 200 at a time. That can introduce batch effects. It's not an elegant solution. The much more elegant solution is using a tool called Genomics DB Imports, which uses a data store, which is kind of like a database format. And that allows you to process all of the samples in one go. It creates this sort of intermediate database that you will then be able to run on to do the final joint calling. These are the commands that you provide. They're fairly straightforward. Combined GVCF, you would just give the GVCFs along with the usual reference and produce the combined GVCF. With Genomics DB import, you will actually give your GVCFs as well. And by the way, here we're enumerating the files in the command to illustrate the process, but you can also just give a text file with the paths to all of the files so that it can be just one argument. Because obviously if you've got 10,000, you're going to run into the limit of how many characters you can put in a command line. So you can just provide a text file list if you need to.
Can you use pattern matching?
Pattern matching.
Like you say, sample.
Yeah. I think you could write a script that handles that as part of your pipeline script. That would be my recommendation.
That will still encounter the character limit for the command line if there are too many. If your glob resolves to too many files, I think you'll still encounter the limit.
Now, what I would recommend doing is loading your data in Terra and putting that in the data model and just running the pipeline on that, and it will handle it on the back end for you.
Genomics DB import will take a sample map file where you have the sample name and then the GVCF path. And combined GVCFs, you can supply the -B with a file that's a list of names.
Yeah, so just to repeat that, there is a sample map option. Basically, there's a few different options for how you can feed in that information. And that's documented in the tool documentation. But yeah, there's options to make things not insane to do this. Yeah.
The DB import thing has a note saying must be run on a single interval at a time. What does that mean?
Yes. So that's actually out of date also as of 4.1. I believe that has been adapted. I'll give the base answer first. What that means is that this tool was designed to only run on a particular interval and process the records that are within that interval. And that really has to do with how the code was engineered initially. And so you would provide the way we provided the intervals was through the pipeline scripts. You generate separate jobs for each interval that is going to run. Now, I believe there have been some changes made so that you can provide a list of intervals and the tool can run with that. Is that correct?
Yeah, so we recently put in, well, our collaborators put in some updates to support exomes. But if you're interested in running an exome where you have hundreds or thousands of intervals in one chunk, there's a special argument that you're going to want to include. But if you want to just do like chromosome 20 and chromosome 21, then that's not such a big deal. It's a question of like how many intervals you supply.
So if I had like whole genome or whole exome data and I wanted to process everything, then I would need to do it by chromosome or something like that?
So we actually have a list for whole genome. The way it's done in our pipeline, correct me if I'm wrong, is that we have a list of intervals within the whole genome that have been designed to lead to a balance in terms of how long the jobs take. Because even if you give like the entire chromosome, that's kind of too big for this. Here we're showing an example with the full chromosome, but in practice, for really operationalizing this kind of thing, we have kind of a designed list of intervals that works well for whole genomes. And it uses things like ends in the genome or places where there's interruption in the sequence to use as kind of natural stopping points.
And I presume in Terra it would happen automatically?
Yeah, all that is already set up and pre-configured, so those interval lists are pre-configured in the workspaces that we provide, so you don't have to worry about that, unless you want to use a different reference. So we are standardized on HG38. I think we've ported some of these to B37, but so if you're doing something very different in that respect, then you have to do some legwork. But if you're doing just a standard thing, that's all preloaded. Okay. Did you want to add something? All right, so once you do that, you will have the actual either Mega GVCF or the Genomics DB intermediate that you can run the JointCalling tool on, and that's called genotype GVCFs. Which again will take either a single GVCF. It can the GATK4 version cannot take multiple GVCFs. It has to be that single GVCF or Genomics DB data store. So if you're running, this is again the two cases, the case where you're running on a single GVCF, the case where you're running on the Genomics DB Workspace, you can see the command is very, very similar. The only big difference, and you'll do this hands-on after the break, is that for working with the Genomics DB Workspace, it's a directory in your file system. And so you provide this prefix stating that this is a Genomics DB Workspace, the name of the directory that was created by the previous tool, and then everything else will just be handled for you. Okay? So that's how you run it. What's going to run internally when you run genotype GVCFs is basically recalculating the qual score for every variant record in the files. This is actually the older model. This is the, and it was honestly doodled on a napkin a while ago, and we never took the time to update it, and I'm glad to say now we don't have to, because there's a different qual model. As of version 4.1, there's a new model that is more appropriate, more robust. And you can read all about it in the blog post that I think David Benjamin wrote. So it's all documented now. We just need to upload this slide. It was literally just a few weeks ago, so forgive us for not being completely... Right, that's true.
Yeah, this became a huge impediment to joint genotyping large cohorts.
Yeah. So, and really what this is doing is giving you kind of a floor of how likely your variant call is. It's really just telling you, okay, this particular call has, if you're above a particular qual score, we're going to say, okay, this is more likely to be something real than complete junk. But it's still, the qual score is not the be-all and end-all of variant quality, despite its name. So this is kind of a first metric that we use for making that initial determination of what we're going to output in the file, but there'll still be quite a lot of work to do to actually look at the distribution of annotations and stuff like that to do the variant filtering in a sophisticated way. Is that fair to say? I don't mean to downplay it, but
it's effectively just accumulating alternate allele evidence, but weighting it by the likelihoods based on base quality and the rest of the aligned read. But yeah, again, it's for sensitivity, and so BQSR for filtering is going to take into account whether we think it's actually a high quality variant.
okay. So now, part of what the tool does, in addition to calculating that qual score, is also adding a number of annotations. Some of the annotations are added by haplotype caller in the original variant calling. Some of them are recalculated and output in the final VCF. And these annotations, and you'll hear a lot more about them this afternoon, are going to help us do that modeling and filtering. And what I'm showing here is the effect of adding many samples to your analysis is that it smooths out the distribution of the annotation values. It basically compensates for kind of chance fluctuations that you might have for various reasons. And so if we're looking at this first panel right here, this is just theoretically how we can imagine the annotation value distribution would look like for a particular annotation where we expect it to kind of center around 0. If we have rare variants or singletons, you can see that the spread of values is pretty wide. Versus the more you have, the more common the variant is within the samples that you're looking at, you're going to have a much tighter distribution because the recalculation across all samples is going to just even out a lot of the disparities. And so what you'll be able to see is that as you tighten that distribution, you get more separation between the distribution you get for good variants, and then that pink curve that shows what you get for a bad variance within this data set. And the goal really, the entire goal of filtering is to increase the gap between those distributions. So you have more separation, and you can make more confident decisions about what to leave out versus what to keep for your analysis. So that's theoretical, and this is showing in practice. If we're looking at, in green, a single sample, annotation values, and then the annotation values for the same sample, but when it's joint called with Nomad, you see that that distribution is much tighter, and therefore you will be able to have more separation on the left-hand side of things that are not to be trusted. Does that make sense? Yeah.
What do you mean by an annotation value? Or in other words, what is the exact?
For example, it might be a statistic that measures strand bias or allele bias in the reads. There's various statistics, and I believe the talk this afternoon will go into more detail of what those represent. But basically, it's statistics summarizing some property of the data like that. Go ahead.
So just looking at the right panel of the slide, does this imply that the smaller red distributions centered around 0, so the mode centered around 0 is the actual true variance, and whatever the large spike on the right is not true? So you're expecting the metric to be centered around 0? Is that the case? Or?
I think in this case, it's shifted. I'm not sure why we have a shift. Laura, do you have any insight?
Consistent between the left and the right panel a bit. I'm not sure which mode of the right distribution is considered to be a true.
Oh, in this case, we consider the right mode to be correct and the left to be incorrect. And it's really this particular, this is a rank sum test where we're basically looking at whether there is a difference in the quality of the evidence for the reference case versus the variant case. And when you have higher higher values, positive values, your variant case is actually more well supported than the reference. So that's why negative values are considered to be indicative of error, because that means that the quality of evidence you have for variance is less than what you have for the reference.
So just looking on the x-axis, it seems like, sorry about maybe being picky, it seems like both modes, like the smaller and the larger mode of the RAND distribution, are on the right. So you claim that only the negative ones are the wrong ones. So like, I'm trying to figure out the separation between the, that we see on the red histogram.
Yeah.
Like, which of that is?
Well, so this is part of the reason that we use a machine learning model, because a lot of the annotation distributions won't actually fit the expected for various reasons, because sometimes there actually is an innate bias in the sequencing. In this particular case, with the read position rank sum, it has to do with the clipping that happens inside haplotype caller and how that's calculated, and there are a couple little sort of particulars about that calculation that tend to not have the.
So to summarize, it's really about how, like, we talk about, we expect the distribution to be centered on 0, and we have expectations about what positive versus negative means. In practice, we may see things shifted because the calculation of the statistic maybe, or the original data has some kind of bias that make it not conform perfectly with the way the statistic is calculated theoretically.
That's right. From what I understand is that the separation, so the fact that there are like 2 modes in the red distribution, is not separating the noise and the signal in that case, right? So you still have to look on the middle left side of the.
It's a lot more separated if you think about it.
It's hard to say. I mean, we don't have any information about these variants in this plot. They're just all variants. And so what we end up doing with machine learning models, we take things that are common, that we assume to be true, and then we see where they lie. And typically they will lie on the more positive mode. And so then you'll get some of that separation based on known things. And these also are not particularly well described just in one dimension. And so once you add in the additional features to the machine learning model, like depth and 2 different measures of strand bias and a mapping quality rank sum, and then just the mean mapping quality, once you take into account all those different features, typically will be much better separation.
Okay, so. Thank you, Laura. That's why having the expert in the room is really nice. Okay, so just very quickly, because we're overdue for coffee. The good thing is hopefully we'll compete a little less with the coffee line over there at the free coffee thing. Anyway, my point is that there was a question yesterday of, at what point do you kind of max out the utility of adding more samples, right? And so Laura did an analysis that pretty much shows us that there's, at low numbers of samples, there's a very rapid gain in terms of how much sensitivity you gain by adding more samples, but it does kind of max out on this set of these were the 120,000 exomes in Nomad, I believe.
One of those points was all of exact, and one of them was a subset.
Yeah, so they're measuring across subsets. So it's basically a titration experiment where measuring on increasingly large subsets, you can see that you kind of saturate around a few hundred samples, and then after that, the gains get more and more marginal. So that's tells you that doing it with even small numbers of samples is worth it. It is definitely worth it. You don't need to have thousands of samples to see the benefits of joint calling. You can already see it at much smaller numbers, and at some point, you kind of max out the benefits. And then the interest of having much larger cohorts is that it brings additional benefits in terms of the analysis that can be done. Any question?
It seems to be dependent from the sequencing platform, right? So more or less.
Largely, yeah. We're not seeing any link
Yeah, I mean,
there.
then you already generate the exact data with all the captures mixed together.
Yeah.
But yeah, you want to explore.
I just get that the NA70 planet example is unmatching, right? So that's the so the red ones are all moved.
Let's take that conversation online for the coffee break, because I do want people to be able to get some kind of caffeine and energy. This is the kind of the flip side question is, well, and this is something that people ask very often, well, if I do a joint calling and seeing things multiple times boosts my confidence, does that mean that I'm going to lose confidence in things that are unique, that are singletons in people? And basically, no, that's not the case. Anything that you would call by itself, you will still be able to call. Now, if there's something that is very poorly supported on the data, you will not be able to call it better, but you're not going to lose anything that you would call if you were calling it by itself. And this is just finally the message that running through this process allows us to scale to really massive scale in terms of, and I think this is already out of date. Yeah, give me the new numbers and I'll put them in the slides. Huh? 144,000. This is a thing of beauty. Okay, I think it's cool. Okay, and that's really it. That's all there is to joint calling.